Bases are not unique. I mean, that was the entire point of the coordinate vector material, that you can have multiple bases, and if you use different bases, you can express vectors in different ways. So, for example, in R2, we have the so-called standard basis. But we're going to see in this section of the textbook that any two linearly independent vectors form a basis of R2. So these sets are all bases. And what these sets have in common, of course, is the number of elements in them. They all have 2 elements, and no basis can have more than 2 elements. Theorem. If a vector space V has a basis containing n elements, then any set in V containing more than n elements is dependent, and hence in particular is not a basis. I'm going to fiddle with the document camera slightly to try to get a little more zoomed in. Now, I know I said in the intro video to this section that I wasn't going to do proofs. I like the proof of this theorem. It provides a nice application of the coordinate vectors. So I will prove this. So the coordinate vectors of these basis elements are vectors in Rn. And this is certainly true, this theorem, in Rn. We proved it as a special case by counting rows and columns. It was in section 4.4, if you want to look that up. So these, sorry, not an N there, a P. So these vectors are linearly dependent, so there exist weights. Not all of them is 0. Such that this linear combination equals the 0 vector. And now we are going to use linearity. We made the statement that the coordinate mapping is linear. So if we apply the coordinate mapping to a linear combination, the coordinate mapping of the sum is the sum of the coordinate mappings, and the constants get pulled out thanks to linearity. So this is a statement of linearity. We've already marked that the coordinate mappings are linear, and now we're going to go in reverse. You see we have the right side of this equality here. Let's rewrite this using linearity. And let's write out that 0 vector. And now remember what the coordinate mapping means. The coordinate mapping of a vector tells you how to express that vector in terms of the basis. So what this is saying is that this vector can be expressed as 0 times the first basis element plus 0 times the second basis element. Oh, hey, it's the 0 vector. They're all 0. This, of course, this is 0. So we have a non-trivial linear combination equal to 0. Ergo, these vectors are dependent just like we wanted them to be.